What I wanted to do is, the message I'm going to give here is very consistent with what Doug is talking about. And I want to talk a little bit about slag and Portland limestone cements and really talk about the relationship that the two of them have when you put them in contact with each other. And I started with the concept that this is really a symbiotic relationship. And I'll tell you, I'll change the title a little bit as we go through. But before we get into this too much, I think really the question is, why are we here? What is it that we want to do? What is it that we're after? And I would ask the question, if you're a person who's, if you're one of the 120 or so friends who's listening right now, you're here because you probably want to make concrete better. You probably want to do what you can to make your impact on the carbon footprint smaller. You want to try something that's got a pretty high level of success. And I would say that if these are the three things that you're really here for, then this is really a good session to be in, because I think we have something that's very useful. As Doug mentioned, there's a lot of opportunities where this has been used. It's been used very successfully, and we think the story behind this and the reasons for doing this are really, really compelling. But the question that a lot of people are going to be faced with is, where do you start if you really want to look at this? Because it's a different material. What's it actually doing when it goes into the system? Do we have data? And I think Doug did a wonderful job of the vast amounts of data that have been collected and really discussing the practical uses in the field. What I'd really like to do is talk a little bit more about some of the background behind this and really start to dive into some of the additional benefits. So, as we hear about this, one of the questions I always get, usually a newspaper is calling or somebody's calling and they're asking about why is cement so bad, because it's producing 7 to 8% of the world's global CO2. And as Doug really pointed out, it's simply just the mass of the materials that we're using. It's the massive volume of material we're using, because on its own, cement and concrete is a relatively low and a relatively good material to be using from a sustainability perspective. And the question that we're going to start asking is, where does the CO2 come from? Well, about half of it comes from the calcination process. The fact that we're going to add materials into the kiln, we're going to calcine, we're going to release CO2. About 40% comes from the combustion process, and about 10% comes from transportation. So as we've mentioned, concrete on its own has a relatively low carbon emission per unit, per mass. However, it's the widespread use that really drives this. And I think what we really need to start thinking about is how we can take simple steps to really make the changes that are needed. And what we're going to be talking about today is a relatively straightforward step, because I think one of the great quotes I took out of Doug's talk is, it looks like concrete. This looks like concrete, it places like concrete, it smells like concrete, it tastes like concrete, it specifies like concrete. People don't know the difference when they're using this material, but there is a difference in performance, generally a similar or improved performance, and there is a huge difference when we start to talk about sustainability. So, we typically look at the fact that there are really three ways that we can make concrete more sustainable from a very easy perspective. We can increase the life cycle performance. We can make the concrete last longer. This is going to mean that we're going to be using less concrete to be replacing it over its life cycle. We can reduce the cement content of the system, so we can reduce the powder content of the system, usually through optimizing our aggregates and really refining our mixture process. But today, what we're really going to be talking about is how we reduce the clinker and get the same bang for our buck. And as we've talked about, this is something that we can be doing right now. This is something that's commercially ready. This is something that's in specifications. So this is something that we're really ready to move into practice very quickly. Now, here are two different cements. So on our left-hand side, we have an ordinary Portland cement. On our right-hand side, we have a cement that has typical clinker shown here in white. We have limestone shown in yellow, and we have our slag shown here in this orangey color. So if you looked at both of these materials, and Doug showed some particle size distributions, and if we looked at these, this is a typical GU cement, as Doug mentioned, or this might be something that's similar to our 595, our 150 cement, something in that range. And on our right-hand side, we're now starting to get into a blended system where, as you notice, as we move from the left-hand side to the right-hand side, we've added some of these yellow particles. So the yellow particles are the limestone. So in our conventional OPC system, We have a little bit of limestone addition, usually around 2 to 3, 4%, somewhere in there. As we move to the right side, now all of a sudden the yellow particles go up, and we get to about a 10 to 12% portion of the system, which is pretty typical. You'll also notice that the yellow particles tend to be smaller, and as Doug mentioned, this is because they grind a little bit easier in the overall system. But this one also has some slag that's been mixed into the system. Now, if we started to test those materials, and we've got reports that go into all the data, and I'm not going to go through all the data because I want to just show that in general, if we look at the left-hand side, what we see here is the heat evolution. We see very similar heats being generated by these materials out at 7 days. Right, we see slightly lower heats with the slag early on. There was a question is, could you use slag cements to drive down some of the high heats at early ages? And the answer is yes, you can do that. And that's one of the reasons why they're being used. But what's really interesting is this is a measure of the reactivity. The heat is a measure of reactivity. And we're getting a very similar reaction that's taking place in the system. But we're getting that similar reaction with a lot less clinker in the overall system. We're getting very similar strengths, as Doug showed. We're getting very similar or slightly improved transport properties when we're using the limestone with the slag in the system. And then there was a question about shrinkage, and we've measured the autogenous shrinkage, and it's very similar. Here you can actually see the shrinkage cracking stresses. Now, this is a very, very high-paced system to try to drive the cracking, because there was a lot of concern with the finer limestone powders. Would these materials be more susceptible to cracking? And what you see is they behave almost identical to the OPC system. So there's really not a huge difference, and we can get into all of the reasons why that's the case, even though it's a finer system. It has to do with the fact that it's really the limestone that's finer in that system. But the big takeaway from this, if we want to just do a quick glimpse of what's happening, we have the powder that's our 150 cement. We have something that's more like our 595 cement or our GUL with slag cement over here. And while they have similar performance, the PLC system on its own is going to have 10%, 10 to 12% less CO2. And when we have the PLC with the slag, we got 40% less clinker, which is putting us at about a 30% reduction in the carbon footprint of that concrete. And this is a major change when you're looking at something that produces concrete with equivalent performance that's ready to go, that's ready to be specified on a daily basis. Right? And the question that a lot of people will ask is this something that's doable? And yes, this is very doable. And as Doug mentioned, in many cases, it's very doneable. There's 10 million tons of this material that's actually been used. There are people who are increasing the use of this, and this is really a great step for us to really move forward. So if you're a big Bob the Builder fan and you're asking the question, are there ways that we can reduce the carbon footprint? Dizzy, the concrete mixer, would tell us, yes, we can fix it. Yes, we can do this. This is something that is very doable, and in fact, in many cases, it's already ready to just start being used on a lot of our projects. Now, as I mentioned earlier, when I gave the title to Drew about 6 months ago, I came up with the title that this was a symbiotic relationship. And then as I started to read about the symbiotic relationship here between the ox and the bird that eats the mites, and so the bird lives off of the mites, and the ox gets the benefits because he doesn't have the mites on him, it said that neither system can live on its own. And I was like, well, that's not really the relationship that we're after. And so I said, well, we may have to change the title of the talk just a little bit. And I remembered back to some earlier commercials. And if you remember some of these commercials from the 1970s and 80s, you had this very dapper young man running around with a big chunk of chocolate. You had this very nice young lady walking around with a bucket of peanut butter. On their own, chocolate is great. Peanut butter is great, but when you put them together, it's really the magic that you have when you put those together to make something like a Reese's peanut butter cup that really makes this even better, and there's a really better relationship when you combine the two. So we're going to change the title of the talk a little bit, and we're going to say that slag and Portland limestone cement is really the peanut butter cups that make concrete better. And that's what we really want to start to talk about. But in order to do this, what I'd like to try to do is motivate some of the computational simulations that I'm going to show you. And what I want to try to, what I want to suggest here is that pores are really the critical factor that's inside of the concrete. right? The pores are going to describe the strength, and the strength is really primarily driven by the capillary porosity, and that's these bigger pores from this picture from Powers almost 70 or 80 years ago, right? The capillary pores are going to be between about 5 nanometers and 10 microns. They're the leftover space that's between the cement particles that's inside of the system. The pores are going to dictate transport, and this is going to be primarily, again, the capillary porosity. They're going to dictate the shrinkage of the overall system. So here we see the little tiny pores. This is the pores in the CSH. The gel pores are really driven by the shrinkage in the overall system. So these are the really tiny pores. And then freeze thaw is going to be driven by these great big pores that we didn't even show, which are the air entrained pores. So again, porosity is going to be very, very crucial for these systems. And almost 80 years ago, Powers and Brownyard developed a model that is really the basis for a lot of what we see in the code. It's a lot of the basis for really how cement developed and how cement properties are explained. And in fact, if you plot porosity, and this is a gel to space ratio, it's a form of porosity that Powers used, it can be directly related to things like strength, like transport properties, like shrinkage when we use the correct models. Now, the reason I point that out is what we want to do is we want to use this plot from Duncan Herford and Thomas Matschei, because this has really been a little bit like the North Star, as Doug mentioned earlier, that it really starts to describe the concept behind using these PLC systems. So the basic idea is we're going to get a certain amount of porosity in the system. Right, if we add a little bit of limestone to the system, we're going to see that porosity decrease because of additional hydration or reaction products that can form, right? However, over time, that porosity will start to go back up. As the porosity decreased, again, remember there's a relationship between porosity and strength. The strength went up, and then as the porosity starts to go up again, you'll see the strength coming back down, almost to a point where you're back to where you started in terms of the equivalent strength. And this happens, not surprisingly, at about 10 to 12% Portland limestone, right? So many people have used this plot and they've said, aha, what we're really after in North America is we want to get similar properties to a 150 cement with our 595 cement at 28 days. Now, what I want to do is I want to take a step into where plots like this come from and see what happens when the system becomes a little bit more complicated when we start adding SCMs into the system, right? So the whole drive behind this is we're going to really try to describe the porosity that's taking place in the system. Before I do that, I want to just get into Powers' model a little bit. And when Powers came up with his model, it was a 942-page treatise on the properties of concrete. And if you read that, you can decipher how to put all the equations together. But shortly after he came up with that, there was a group out of Scandinavia that said, you know, you could do this graphically, and it could help people to understand all of the intricacies of what you're talking about. And one of the really nice things that they did is they reformulated the equations that Powers had developed. And they essentially said that there's a linear relationship that takes place. And that linear relationship is based only on two things: the initial porosity, P, and the degree of hydration or the extent of reaction, alpha. So if we look at this plot, we start out before the system reacts and we have cement, shown here in the gray. We have water shown here as blue, right? And we have our initial porosity, which is about 61% in this particular case. So all of these equations are driven by putting 61% in here for P, right? And letting alpha vary from no hydration to as much hydration as we could have in the overall system. Now, as we react cement with water, the cement gets used up and is reduced. The water gets used up and is reduced. And really three things start to form. We get this thing called chemical shrinkage, which is a slight volume reduction that we're not going to worry about today. We get this thing called gel pores, right? These are the little tiny pores. And we get the hydrated cement paste products, right? Now, the leftover space, the leftover water, this is going to be our capillary porosity. And while Powers developed this model, and while it was incredibly important 80 years ago that everything was linear and could be calculated very simply, the one shortcoming of this model is it only considers water and cement. It doesn't consider what happens if you add limestone to the system. It doesn't consider what happens if you add fly ash to the system. It doesn't consider what happens when you start adding other things to the system. So we needed to be able to take this a step further. And this is one of the things that we've been working on. And now I'll remember to mention, this is a lot of work that's going on at Oregon State. There's a lot of work that's going on around the world in this particular topic. What I really want to do is I want to talk about the fact that this can be used as an extension of the Powers and Brownyard model. And it's going to allow us to extend what Powers and Brownyard were doing, but to now start to include supplementary cementitious materials. Now to start to include industrial byproducts. So you may say, I've got this really wild powder. Can I figure out if it can be used in concrete? This is an approach to do this. Maybe you have ponded ash. Maybe you have something else that you've dug up. This is a way that this can be done. And this model, which is actually led by Burkhan Isgor out of Oregon State for the work that we're doing here, right, uses a technique called Gibbs energy minimization to predict the reacted products. So this is something that is really, really useful to be able to do. And what we want to do here is we want to get into a little bit of how this works. Right, so a lot of the early work here was done by EMPA, which is a Swiss group, and Barbara Lochenbach's group. But what you'll see here is this has striking similarities to what Powers and Brownyard were doing. So with no hydration, we have cement. Now here, cement is not just a big gray blob. It's essentially everything from this triangle on down. Because what we're going to do is we're going to consider all of the different components of the cement. So we've got the A-lite, we've got the B-lite, we've got the aluminate, we've got the ferrite phases, we've got some silica, right? We have all these different phases in our cementitious system. So now we can consider those. We have the water that's in the system, now it's shown as aqua. And as those systems react, again, we get that chemical shrinkage we saw before. All right, that was that orange on the other plot. And we get these reaction products that are forming. But now instead of just saying they're overall reaction products, we can actually say this is CSH, right? The green stuff here, this is calcium hydroxide, right? We can look into this and we can start to talk about monosulfate forming. And we can talk about the other phases forming. So this gives us more information on what's happening. It also gives us the ability to consider alternative systems, which can be very, very powerful. So you're probably thinking to yourself, well, this has to be magic that causes this to happen. Well, it's not really magic. It's really thermodynamics, right? And this is a really well-established set of rules. Yesterday, Keshav gave a great talk about how this is a well-established set of rules, and he talked about how this could be used for fly ash. Today, we're going to talk about how this could be used for slag. It's the same approach, and the goal is really to allow us to determine the reaction products that form if we know the chemistry of the initial constituents. And what we're going to talk about is this is a lot like putting together a puzzle. And what we're doing is figuring out where all the pieces fit together the best, right? It's like putting together a puzzle. It's like playing Tetris. The whole idea is to find the lowest energy state in the system. So what does that actually mean, and what's a practical example of this? So let's consider that we have 1,000 grams of OPC and 400 grams of water. We could break that OPC up into components. So we could say it's got a certain amount of C2S, it's got a certain amount of C3S, C2S, C3A, our ferrite phases, right? We can break this down into the initial constituents just like you saw on the previous graph. And we can ask the question, right, what is a feasible combination of reaction products that are going to occur when you put these materials together with water? So how much CSH is going to be produced, how much calcium hydroxide, how much of our monosulfate, right? And then what's left over in the pore solution. Now, we could do this using the approach I'm going to describe, and it turns out that we're going to use a set of rules that are a little bit more sophisticated than what I'm going to mention here. But if we guessed the answers, right? We could guess that 500 grams of CSH are formed, 400 grams of calcium hydroxide on down, and we could calculate the energy of the system, right? And there's a certain energy associated with this. But we could then flip the stage a little bit and we could say, what if we guessed another set of outputs? We would have a slightly different energy state. And we would be going to a lower energy state. And much like me on a Saturday when there might be some baseball games on, right? I want to get on the couch and I want to get into the lowest energy state I can possibly get into, right? Here we're going to find out that we're going to see the lowest energy state is going to be the most feasible set of reaction products. So we could keep changing the reaction products and keep changing the reaction products, but at some point we're going to find the optimal reaction products, the lowest energy state, and this is actually what we would expect to be produced at equilibrium. Now, as mentioned, this approach has been used, and it's been used by groups around the world. Barbara Lochenbach's group has been using it. Burkhan's been using it quite substantially. There's lots of other groups who have been using this. The real thing is that this has been compared and compared and compared to experimental outputs, and this is really a great way that this can be pushed forward. The second thing that we're going to be able to do here, and we're going to start to talk about, is while GEMS tells us the reacted products, it doesn't really tell us about how we segment the pores in the system. And there was a question that popped in here that asked about kinetics, and we have a series of kinetic rules. I won't get into that as we get into this, but there are a series of kinetic rules that we go through. Parrott and Kilo developed these rules in the 80s. We've actually modified the rules to allow us to bring other supplementary materials into the system. I can send information if you'd like some information on those, but that is an important component of this, or an important piece of this. But this provides the volumes of the materials, but it doesn't really tell us how they're broken up into different pore sizes, right? So what we want to do is we want to talk a little bit about this, all right? And what I want to mention is we've actually used an approach that really takes exactly what Powers did, and it overlays it on the outputs that we would get from energy minimization. So here you can see, again, Powers is shown on the right-hand side, the gray from the cement, the blue from the capillary water, the gel water here shown in aqua, the gel solid shown here in yellow. And we can take the GEMS output and we can map these directly to the types of pores and the types of phases that we have from Powers' model. So the cement is relatively easy. The capillary water is relatively easy. For gel water, we do some accounting to figure out which of these phases give up water, and then we take a portion of the remaining water and we put that into the system, and we have a system that correlates really well. So the orange lines here are the prediction through GEMS using something we call a pore partitioning model. The color in the background is Powers' model, and there's a very strong correlation between the two. Now, how do we use this to predict some of the results that we're talking about here? So again, remember, this is that plot from Matt Shai and Herford, all right, where they said, you know, initially we're going to see a decrease in the porosity of the system. When we do this in the model, we see that exact same decrease, right? We see a slight increase in the porosity, and again, we take this out. Now, we go out to a value of about 18%. And part of the reason is they didn't actually start at 0 when they actually ran some of these calculations, which is kind of interesting. But we see a very, very similar type of behavior here. So this is telling us that at least for the standard system, we're on the right path. Now, how does all of this get put together? And I think this is really where this whole thing starts to really come together and tell a really nice and interesting story. So we can take the original amount of the OPC and the chemical composition of the system, right? And we can put that together with our SCMs in the system. So we need to know things like the chemistry. We need to know things like the kinetics, but we also need to know how much of the material is going to actually react. And for this, we determine this from a Pozolonic reactivity test, which is similar in nature to the R3 test, but it's actually designed specifically to tell us about the Pozolonic reaction. All we want to know about out of that test is the Pozolonic reaction. So we put calcium hydroxide, pore solution, and our whatever material we're after into a system, and we figure out how much of that system is going to react. And we use that as an input into this model. The second thing we're going to do, and this was a great question from Chuck, is this is where we're going to bring in some kinetics rules. We're going to bring in kinetic models that consider OPC, and again, this is from Parrott and Killoy, and we're going to modify that to account for some of the SCMs, and there's been several papers by Deb Glosser and Burkhan that have really driven this. And we're going to now run the model, and we're going to predict the solid phases, the pores, and the pore solution chemistries that come out of this. Once we have this for paste, we can actually now drive this a step forward. So we've got the output from paste. We can actually scale this up by adding aggregate into the system. And all of a sudden now, as Keshav mentioned in his talk yesterday, we have a very powerful tool because we can start to predict things like concrete resistivity and formation factor. We can start to predict the overall porosity. We can start to predict the overall strength. We can start to predict freeze-thaw performance. We can start to predict things like sulfate damage, right? There's lots of different types of simulations that can be done as we start to pull all of this together and we start to tell the overall story. So let's talk a little bit about some of the questions as this relates to PLC and then PLC with slag in the system. So up to this point, I've talked a little bit about the tool. Now let's talk about how this tool can start to answer some of the questions. One of the first questions that we got was, is there a big difference between a type 1 or a type 3 system and a type 2, type 5 system? Depending upon where you're at in the country, all right, you may see a slightly different clinker composition. So what's the impact of that clinker composition? What's the impact when it comes to porosity? So here you can see one of the predictions that's made. On the top, we have a 2.5 clinker. All right, on the bottom, we have the reacted phases that actually form out of this. Again, the basic issue here is that as we add limestone into the system, it's going to change some of the phases that are forming. So what you notice here is as we add limestone in, especially at lower levels, right, you're going to see this monosulfate is going to essentially be converted over into monocarbonate, which is shown here in yellow, and we're going to see more ettringite forming in the system. So what you're going to notice is this point here, right, corresponds to that point of minimum porosity, minimum amount of solution in the system, right? And that's really due to the phases that are forming in the overall system. And as we start to move away from 2 to 3% limestone, all of the phases that are forming now as we move to the right-hand side, they're all the same phases, right? We're left over with a little bit of unreacted limestone or unreacted calcite in the overall system. So the whole thing that we're showing here is we have slightly lower calcium hydroxide when we've got limestone in the system. We've got ettringite and monocarbonate phases that are forming, and we saw the porosity decrease as we added a little bit of limestone in the system, primarily due to the monosulfate conversion in the overall case. Now, if we compare the type 1.5 or 1.3 shown on the bottom clinker and 2.5 shown here on the top, right, what we notice is the plots look incredibly similar. So even though the clinker has slightly less alumina, this is really overblown in a lot of these discussions, and there's not a huge difference in the way these two clinkers behave. So if we now look at sort of the overall porosity in these systems, what we can see, if we look at these sort of average systems that are coming out, we can see that they're the type 1.3 is shown here in red. The type 2.5 is shown here in black. We can see that even though there's slight differences in the clinker that's used to make these materials, they're very, very similar in terms of their overall porosity and the overall reactions that we're going to get into these systems. All right, so again, the takeaway, porosity decreases as you add a little bit of limestone into the system, but the porosity really isn't that much different if we look at different types of clinker that are used to make our OPC. The second question is really what happens now when you start to add ideal SCMs into the system. So maybe you want to add silica dioxide, or maybe you want to add alumina to these systems. How does that have an impact? And this is going to be really important, because what this is going to get back to, and what this is really going to help us to understand, is that all SCMs are not created equal. Some are going to bring more silica to the party, some are going to bring more alumina to the party, some are going to react more. We really have to ask, what is the SCM, or what is the industrial material that we're adding in? What is that bringing to the overall system? So the first thing I want to do is I want to talk a little bit about what happens when you have Portland limestone and just a pure silica. So this may be something like a silica fume. I'm going to show you several of these plots on the right-hand side, so I want to take a few seconds and I want to go through these. I think Keshav did a great job of putting a lot of information on a plot that's I think helps us to really tell a story. On our x-axis, we have the limestone content that we might have. So we've got 0 limestone over here at the origin. We get up to about 30% limestone if we go all the way out to the far end of the x-axis. PLCs are kind of shown here as this purple dash, and ordinary Portland cements are kind of in this reddish region. But if we have no limestone in the system, we've got about 38 to 39% porosity. Now, if we look over on this bar on the right-hand side, it's just a color-coded map of high porosity, which is yellow. This is kind of our classic clinker system. And then if we get down to really low porosity, we get into these blue ranges. And not surprisingly, as we add a little bit of limestone, as we've seen, the porosity decreases, and then the porosity starts to go back up. But at all of these points here, we're only at about 37% porosity, where if we used our clinker, we're at about 39% porosity. So everything is slightly lower than what we had originally. The other thing that I'll mention specifically with the silica system, at silica values typically below about 20%, this is where we're going to still have calcium hydroxide in the overall system. You'll see that these contour lines are relatively straight up and down, which means that there's not a huge impact of the silica in the system, right? So the silica is going to be reacting with the calcium hydroxide. It's going to form more CSH, right? We're going to have very similar porosity, but a refined microstructure. It's really not reacting with the limestone, not reacting with the carbonates. So it's not going to have a huge impact on the overall porosity. We see that the limestone in general decreases the porosity slightly, but in general, we get a very, very similar behavior irrespective of the amount of silica that's in the system. However, when we add alumina, we have some of those additional reactions that we were talking about. And if we add alumina, this is the overall porosity that we're going to start to see in the system. What we're going to notice is that the calcium hydroxide and CSH are going to form more cash phases. They're going to form more calcio-alumina silica hydrates in the system. This is going to lower the porosity. So if we had just a straight system without additional alumina, we'd be at this black line. But as we add alumina into the system, as we add more and more system, there's more alumina react with the carbonates, and we can see this porosity really decrease substantially, right? And we can see this really cause a great impact. The other thing that we notice now is while our 0 line may be here, and we may have seen sort of a similar performance around the 15 to 18% range for our conventional Portland cement systems, now when we start adding slag, we could possibly go to much higher limestone contents where we could really see some of these behaviors really improve. If we look at this plot, it gets slightly more interesting than when we looked at the silica system plot, because what you'll notice is, again, at 0, we have about that 39% porosity. But what you'll see here is now instead of the contour line sort of marching linearly across the plot, what we really notice is by adding some of the alumina into the system, we really get kind of a trough type behavior with very low porosities. And I've, of course, chosen the incredibly wrong color. So let me change the ink color here. And you get a very, very low porosity really in these ranges here, right? Where you're seeing a huge benefit of that alumina reaction in the system, all right? And this is really going to be very beneficial when we talk about what happens when you add metakaolins, when you add slags, when you add any alumina-bearing phases into the system. As mentioned, we can also do other sorts of calculations. We can calculate the amount of calcium hydroxide in the system. So we can show you that calcium hydroxide is depleted when you get to a silica system of above about 20%. We can see that that's also going to happen in the alumina system. We can see what happens to the pH of the pore solution. So this would have impacts on things like corrosion resistance or ASR. But what you notice here is the pH changes slightly, but it doesn't increase in any way when you start to use your PLC. In fact, there's a slight decrease in the system. So again, the real takeaway: silica doesn't have a huge impact with the limestone and really has a minimal impact on the phases and porosity. Alumina, however, does have a major potential to react and actually creates a substantially lower porosity in the overall system. So now the question really is, what happens when we add slag and PLC together? And this again is a case where we started to add this into the system because remember, slag is now containing about 35% silica, 10% of alumina, and 40% calcium in the system. Our slags typically measure out to have a reactivity of around 60% using that Pozolonic reactivity test, where we actually account for both the pozolonic and the hydraulic reactivity. And what we can now start to see is we see, again, as we add limestone, the porosity decreases, and then we'll go slightly back up as we increase the higher and higher levels. But in all of these regions, the porosity is actually lower than it was for the ordinary system on its own. And while the slag doesn't significantly affect the porosity, it does start to change how those pore phases are distributed, and it does start to change some of the reaction products, making them much more stable as a function of time. So again, our takeaway here is slag really can help to improve performance. It's actually starting to decrease the porosity in the system, but we don't see that huge benefit we saw with just straight alumina, partially because of the partial reaction and partially because of the fact that slag isn't 100% alumina. But what we see is a very similar type of porosity, but we do see some benefits when you get out to higher and higher values. We also see that the slag is stabilizing more of those phases because of the reaction with alumina in those systems. So we really wanted to do some work, and we've been doing a lot of work. A report is going to be coming out in the next 3 months or so, where we've really compared about 80 different mixtures looking at OPCs and PLCs together. But the basic thing that I just wanted to mention is, again, when you start adding alumina into these systems, you get more benefit because you're reacting with more of the limestone and more of the calcite that's in the system. So I don't want to get into a lot of the experimental design issues here, but we looked at plain systems. We've looked at systems with fly ash. And I'm going to change this color back again to something that we can see. Plain systems, systems with fly ash, systems with fly ash and silica fume, systems with slag, slag and fly ash, and then some natural pozzolans. And what you'll notice is there's a certain amount of calcite that's available, shown sort of in this in the whitish in the background, but the alumina that's available is shown in the grayish color. And if we look at this plot on our right-hand side, the more alumina you have in the system, the more it's going to react with the calcium carbonate, the more it's going to form those carboaluminate phases. Now, if the limestone doesn't react, it's going to stay as a powder. It's going to stay as a solid product in the system. But if it does react, it's going to actually help us. And here you can see the most reactive of all these phases are the ones that are actually containing slag in the overall system. If we compare the porosity from the model to the experiments, what we'll notice here is the model predicted porosity versus the experimentally measured porosity. We see that the experimentally is measured is about 2% higher. What I do want to point out is that the model doesn't account for entrapped air. Once you account for 2 or 3% entrapped air, this is a direct comparison, and it works for every single mixture except for one mix where we believe there may have been some consolidation issues. We now start to do a direct comparison where we compare the amount of calcium hydroxide consumed. And what we notice here is as you start to get more of your siliceous materials into the system, we're going to be consuming more calcium hydroxide. But again, we've had very, very good comparison between the model, the experiments, and what we're seeing with the OPC. Now, one of the other things that I will mention here is we're going to compare the aluminates and we're going to compare the CSH from an OPC system to a PLC system. And what was initially a little bit surprising to me is we see a slightly lower amount of CSH when we have PLC in the system compared to OPC. But this is when you look at it as the overall system. And the real takeaway from this is we would expect to have slightly lower CSH. In fact, we'd have 10% lower or 12% lower CSH if we just base this on dilution. But we don't have 10% lower, we have more like a 5% lower value. And this is telling us that we're getting about 5% more of the clinker reacting to form CSH. And we have a similar story with our carboaluminates. So again, the takeaway, the fourth takeaway is that the models are generally agreeing very well with the experimental observation. The calcite that's reacting is directly proportional to the reactive aluminate in the system. And all the evidence that we've seen is that PLC can really be used as a direct replacement for the OPC in almost every cases. Now, the last piece of this, and I don't know why I didn't give this its own bullet, because this is one of the most important pieces of what I'm going to mention here, is we've seen a lot of concern and people asking the question, well, if I use PLC, can I also use an SCM? And the answer to that is unequivocally yes, right? PLCs are going to work better with SCMs in general than the OPCs. So there's a huge value of putting that peanut butter and chocolate together to get the Reese's peanut butter cup, because of the alumina that's in that system. There's really not a downside. There's really only an upside when we start to look at that. So in summary, and we'll then start to go to questions, Portland limestone cement and slag can be really used together in a very, very compelling way to have a substantial reduction on CO2 or substantial improvement on the CO2 footprint. This is something that's immediate. This is something that's now. This is something that we can start using today, which can have a huge impact on the carbon footprint and really be beneficial for the overall industry. There are substantial commercially available solutions that are available. As Doug mentioned, this is really leading into specifications. This is ready to be used in codes. This is something that's really ready, and it's an off-the-shelf solution to really help about that, to help the overall process. It's really all about porosity. And what we've shown is a thermodynamic modeling tool that really builds on things that have been in the concrete industry for 80 years, but it takes them from OPC to really start considering PLC, slag, fly ash, silica fume, right? Limestone and slag are really like the peanut butter and chocolate, right? On their own, they're good, but when you put them together, you get that peanut butter cup that's really the overall beneficial system. And it's really the alumina that's in the slag that really gives you that bang for the buck, and that's really what you're after. Again, what I'd like to do is I'd like to thank Doug for a great talk to introduce the session. I'd like to thank Drew and his team for organizing this, as well as all the co-authors who worked on this, with Keshav doing lots of the modeling, and really Burkon leading our modeling effort. And with that, Drew, I don't know if there's a time for questions, but I'd be happy to do that if we can.
Yeah, we have a few questions I want to address from the previous presentation as well. Thank you, Professor Weiss, for this. I think it was a great presentation and took into account what Professor Hooten had to say as well. First of all, let me pull up the questions really quick. The reaction rates of these phases will be different and also related to the surface area and the volume of each phase. How is that addressed? This was in the chat, so maybe we can bring people up if they would like to chat with Professor Weiss. We do have about 15 minutes, so I don't know if that was a sufficient question or you would like me to get more from them.
Sure. So Neil, if I can go ahead and start to answer this. The question here is about how reactive the materials are going to be. So all of the models that we're talking about are really being driven to an equilibrium state when we show this. So it's really, everything's being driven to that long-term value. The kinetic effects are really going to be what's going to describe things like surface area and some of those other items. So surface area is actually built into the kinetic models, and surface area comes into those components. And it says silica fume seems to do better than expected. I think one of the reasons that the silica fume is doing well in the system is it's reacting with our calcium hydroxide in the system, which is what we would expect to have in those cases. The slide showing a number of different mixtures showed slag and ash mixtures, where the slag performance significantly higher than ash. What was the alumina content of the ash? If the alumina content of the ash is higher, but the performance is lower, how is that explained? So the interesting thing is, I'll try to answer some of these questions and then add a little bit of context to this. We did look at a couple different ashes, and I would have to get back to you with the exact alumina contents of those ashes. The ashes are much more variable than the slag. The slags are very, very consistent in terms of their reactivity and the benefits that you see. So the real takeaway on this is, both of them can show benefits. The ashes tend to be more variable, and it may be due to the alumina, but I think it has more to do with the reactivity of the ashes. Most of the ashes that we test have a reactivity of somewhere between about 20 and about 45%. And we've now tested about 80 different ashes, and they fall in those ranges. And so that's one of the reasons why you tend to see more variability with the ash. And Matt, if there's other questions on that, I'd be happy to answer those. Mahir asked a really good question that was, is this grade 100 or 120 slag? And I would say we get very similar performance from both of those. And there was actually a pretty good discussion yesterday with slag folks about really how much of a difference those grades are making. There's a little bit of a speed difference with the 120s, but the 100s work really, really well for what we're trying to do here.
Thank you. I want to make sure we got to address Professor Hooten's question directed towards him in the chat. Do you feel like we answered that in the chat, Doug, or do you want to address that? Specifically, the question was, we have encountered high early strength and lower later strength and are concerned about early heat generation. How can Portland cement, limestone or slag cement be best used in mass concrete?
Yeah, I don't know if I answered the trouble is that I don't have enough information to answer the question.
Okay.
We don't know I don't know if everything's equal. He's saying the question was in the chat box was, sometimes they're seeing with limestone cement higher heat, higher strength at early ages, and so what about mass concrete? And my thought was, well, if everything else is equal, and it could be cement specific, some cements may react faster with limestone than others, but if you had to in mass concrete, you'd probably increase the slag content to reduce the heat. But that's my off the cuff answer.
All right, I'm actually gonna invite them on if they want to ask or provide more specifics, and see if they will. Are there any other questions while we're waiting there? One comment: my daughter hates peanut butter and chocolate together, so apparently the analogy isn't working across the board.
She can't be a true Weiss then, Chuck. That's not going to work if you don't like peanut butter and chocolate together. I was going to mention to someone else that the Keyshav was nice enough to send the alumina contents for the fly ash and the slag. The alumina in the ash was 21%, but as mentioned, the reactivity was lower, where the alumina in the slag was 12% with a higher reactivity.